Hello, my name is Lee Floria. I am with the Washington State Geological Survey in Olympia, Washington. I am giving this presentation today in place of the presentation that was submitted by Sarah Burgess back in 2019 in preparation for this Congress, which of course has since been delayed. The presentation that she was planning to submit and be present for was on her master's degree work at Indiana University on sulfur systematics in the Mitchell Plateau. That data and the conclusions of that work are a subset of what I will present to you today, which has been sort of an expansion of that work in the past couple of years and evolving into sort of a more broader holistic view of what her and I and some others are thinking of karst in the eastern United States today. My co-authors, of course, on this are Sarah Burgess, who should be the one giving the presentation today, and Tracy Branham, who remains at the Indiana Geological Water Survey as their geochemist in-house. So today, I hope to give you a flavor of what that work was and give you some additional context. There have been other papers and presentations that have been given. You see in this list, for example, the middle on that list is what you were supposed to be listening to today. So with that said, let me take a step back where this journey started for me in 2000 and note that there's an interlude of Florida that will interestingly come back briefly towards the end of this presentation. But back in 2000, I was living in Kentucky and mapping caves with others. And one of the things that we did was sort of discover that the caves in this part of Kentucky had an alignment, and that alignment was along a set of fractures that were associated with a deep basement fault as part of the Rome Trough, which is a failed rift zone that developed at the end of the Ediacaran at the beginning of the Cambrian period as a failed rift zone of the Iaptus Ocean, and that has since filled with Paleozoic sediments. So to kind of reorient you, when I came back in 2008, I started working in southern Kentucky. You see in the inset image, the state of Kentucky. The blue is the carbonate exposure, and we're effectively on the Tennessee state line in southernmost Kentucky. And on this map, you can see in red the set of cave passages that have been mapped over the past 20 years. Which accumulates as about 60 kilometers of cave, and then some of the key structural features, most important of which is the Sunnybrook anticline, which we will come back to in a few. But in these studies from about 2008 to 2015, the question was, can we incorporate geochemistry into our understanding of the evolution of these caves in a more comprehensive way? So of real interest to me was the role of sulfur, and that came up because some of these base level streams, such as the image that you see on Beaver Creek near some of our cave survey projects, had blooms of sulfur oxidizing bacteria, which is the white that you see, and residual bitumen from oil seeps, which is the black that you see. And these were very numerous. And so we did a series of collections of samples from various caves and various springs, looking at how the chemical profile aligns along what kind of sourcing that there was for data. This area was very impacted by the early oil industry. And by early, I mean effectively the late 1800s to the early 1900s, ending around 1920 to 1930, when the reservoir pressures were depleted such that oil was just not economically feasible. And so we know that there was significant oil production and development in shallow strata. And if we look at the data from the caves, we can run a principal component analyses on the chemistry of these data, and we see that there are multiple factors that explain the chemistry of these sites. In these two principal component analyses that you see, the axis, which would be factor 2, is the vertical axis, or factor 2. It comprises largely those analytes that are the result of carbonate acids or carbonic acid speleogenesis. So you have your calcium, your magnesium, your bicarbonate, the nutrients that come in through meteoric recharge. And so those are sort of co-evolving. And then on your x-axis, that explains about 31% of the data, we see other factors that are not necessarily aligned with that carbonic acid signal, such as sodium and chlorine and total organic carbon and sulfate, which points to a secondary process. And I'll argue that that secondary process is sulfuric acid speleogenesis. And so we used in 2013 to 2015, we used those data to be able to better partition the amount of carbonate and therefore carbon dioxide that was being mobilized from the atmosphere into the recharge and into the karst system and moved through, as compared to the amount of carbon that was being derived from the bedrock, from the solution of that bedrock and moving out of the system. And by partitioning that based upon the chemistry and association with how much was sulfur derived versus how much carbon was sulfur derived versus how much was carbonic acid derived, we could then develop a landscape evolution model that did a fairly good job at replicating the timing of cave levels in this part of eastern Kentucky, the Cumberland Plateau, as had also been done through cosmogenic age dating of sediments inside those caves, such that we have staged incision during Pliocene age glaciation. Sort of the known story and another way to affirm that process. So that was that work. And then moving sort of the concepts of how to conduct these detailed chemical investigations of sites over longer periods, we translated to the Mitchell Plateau in the same age of rocks, but now in southern Indiana, as you can see in the inset. These are basically the same sort of layout as sort of Mammoth Cave, which is a couple 100 kilometers to the south. But now we have more proximal to the glacial margin. The rock units are thinner, and we have other glacial processes involved in sort of the landscape evolution. So here we developed a study that involved 4 key sites in the Blue Spring and Lost River karst basins, which are south of the city of Bloomington, which is where Indiana University is located. Those 4 sites labeled on here were Blue Spring Caverns, where we sampled for 2 years at the boat dock in the cave. It's a commercial tourist cave. Flood Creek in the Lost River watershed, which is an ephemeral surface sinking stream that discharges from agricultural fields into the subsurface. Wesley Chapel Gulf, which is a karst window where the Lost River rises briefly into a collapsed sinkhole, flows across the surface, and then back into the subsurface. And then Orangeville Rise, which is one of the 2 rises of water from the Lost River Karst Basin. And so we monitor these with every 15 minutes, and we did sampling of these sites every 2 weeks for 2 years. I'm only going to show you the portion of these which are the sampling every 2 weeks. So, and I'm only showing you a subset of these data to make a point about the process. So on the top, we have the specific conductance of each of these 4 sites over a 2-year window, and the gray vertical bars are the rainfall. So you see as labeled the dry season for each 2019 and 2020 labeled here, and then the 4 sites. And the point to make here is that you can see that both both Orangeville Rise and Blue Spring Caverns are more elevated in their specific conductance, but Orangeville Rise specific conductance greatly rises during the dry season comparatively to where it exceeds the value you see at Blue Spring Caverns. And the reason for that is the large introduction of dissolved sulfate into the water at Orangeville Rise on the bottom graph. So you can see that while Flood Creek and Wesley Chapel Gulf have fairly low, almost background levels of sulfate, Blue Spring Caverns rises in sulfate concentration during the dry season, and Orangeville Rise greatly rises during the dry season. But what's interesting is that part was known for a long time. What Sarah in particular added to this was looking at the isotopic composition of that sulfate through time, and then performing a mass balance of the in-member mixing model to be able to assess how much of the sulfur came from each source. So here we have on the top left, the sulfur isotope composition of Orangeville Rise in orange and Blue Spring Caverns in blue. And you'll see that the Orangeville Rise asymptotes in its isotopic profile with increasing sulfate concentration to what is known from the anhydrites that are located in the St. Louis limestone, which is one of the rock units that host these caves. And so the idea, which was known before, is that the sulfate at that location is associated with the evaporites. But if you look at Blue Spring Caverns, it does not follow that trend. In fact, it is linear in the opposite direction, such that it is moving towards more negative isotopic compositions with increasing sulfate concentration. And after locating, thanks to the tour guides, some petroleum seeps in the cave, we've sampled the hydrogen sulfide coming out of those seeps and see that there is a linear mixing between meteoric sulfate and oxidized sulfate from these hydrogen sulfide seeps. And so performing this mass balance and in-member mixing model, Sarah was able to estimate that at peak concentration, about 61% of the sulfate can be attributed to the sulfur emerging in these petroleum seeps in the cave. And the implications to what that means for speleogenesis are rather high. And in short, it is clear that the sulfur has some element of involvement in the evolution of these caves. They are network maze caves. There are sulfur seeps in them, and gypsum that is located above in drier passages has very depleted values of sulfur isotopes, which have a connection then to the hydrogen sulfide being degassed from these seeps. And so here we find a situation where both in Kentucky and in here, sulfur seems to have some significant influence in the evolution of these caves. But moreover, this is a regional trend, because if you look at the data from 104 springs in the Mitchell Plateau, from north of Bloomington, Indiana, all the way down into the Ohio River, we find clusters of springs that aggregate towards types of water that are in the system. By and large, most of these springs are meteoric waters that react with bedrock through carbonate acid speleogenesis and discharge at springs. But there are some springs that have an intermediate signal with high specific conductance and higher than average sulfur concentration that seem to be collecting water from deeper sources. And those deeper sources split between those that are like the springs that are coming out of evaporite type systems like Orangeville Rise, and those that are coming out of mineral springs, largely from deeper sources, in many cases associated with basin brines and petroleum reservoirs, such as at French Lick. And so we find two different pathways that these springs follow that indicate mixing with those two types of deeper water end members. And so this is a regional signal that we find. So now let's go back to Kentucky again after a few more years and look at this again, but through the lens of a different cave near to the one that you saw sampling from earlier. In fact, when you see this image and where you see the words Otter Creek Valley, that word otter in Otter Creek Valley is the site of the spring from which you saw that earlier study. So we're really quite close. But the geology is different. This is along that Sunnybrook anticline from that figure earlier in this presentation. The image at the right is the geologic map of this area as published by the Geological Survey in Kentucky. We did more geologic mapping and did some more detailed analysis of the cave and found that the tectonics were considerably more complex than presented on this geologic map. We found slicken sides that indicated transverse motion, basically a left lateral slip, and that we had high deformation and fracturing zones on one side, which indicated oblique compression, such as this. And so the way that we attributed that forming we'll get to in a moment, but is related to end Paleozoic tectonics at the end of sort of the Appalachian origin. But now if the cave itself is geochemically really interesting, in many ways, it follows the process of older conduit systems from Otter Creek that have been pirated by more recent systems that are coming from Vados recharge and vertical shafts, and mixing with, we have, again, petroleum seeps in the base of the cave, as seen in the images on the right, that mix, and that water then flows out to Otter Creek today at modern base level springs. The level of petroleum entering this cave is considerably larger than any of the other examples that you've seen before. In fact, the image in the lower right is of Sarah dipping her finger in free product that filled her footprint from the week before. So just to give you an idea of the rate of flow of this petroleum into this aqueous system. Also in this cave, we find very interesting sedimentary structures that are clearly related to ancient paleokarst. This is an example from not far away where you can see the outline of the paleokarst feature shown. These are very much morphologically similar to the flank margin cave type features you find in the Bahamas, or like what we saw in Florida with these stratiform type caves that are associated with paleo water tables. When you look at them more closely, you find that they are dolotomized. They are, in fact, in some cases have dedolotomization, and that dolomite is been fractured heavily. You have crystallization inside those fractures into a pseudo boxwork with large spar. And then you also have associated with that Mississippi Valley type deposits with copper and zinc and iron type minerals that are embedded in these calcite bugs and calcite spar. Morphologically, as I said, they're very similar to what you see in Florida, which creates an interesting sort of counterexample to the type of caves that you find today. So now I want to take 2 slides and summarize this flow chart of what we think happened. Initially, you had this failing Iaptis rifting along the Grenville structure, forming the Rome Trough and a sediment depot center, which in the Paleozoic became a hotspot for carbonate sedimentation in these epiric platforms, creating these large exposures of Mississippian, well, effectively Cambrian through Mississippian age carbonates, a focus of which for us has been the Mississippian. And these basins are very expansive. As we move forward into the late Mississippian, we have these cycles of transgression and regression that create exposure surfaces in the Mississippian carbonates. Those exposure surfaces are creating paleokarst that fills with sediments. Those sediments then are exposed to reflux brines, which cause dolotomization. As we move into the Pennsylvanian and we have regression and this fluvial deposition of sediments from the growing Appalachian Mountains, killing the carbonate platform, we see meteoric recharge, flushing, and causing detolatomization of these cave-filling sediments. Then at the end of the Paleozoic, in the early Permian, we see endorogenic distal tectonics that create these low amplitude fold tracks, such as the Sunnybrook anticline, and this oblique compression causes some faulting to occur like we see at the Sunnybrook site. Then we have long stability. That long stability occurs while MVT deposits are being mobilized and moved through the system. And then we have Pliopleistocene age incision, which is creating the caves we crawl through today, and then flushing of these petroleum reservoirs by meteoric waters, and then anthropogenic effects from today and pumping of those reservoirs to where we have a 4-dimensional puzzle today, which is reasonably hard to decipher. But the sulfur is a key to the understanding of what's happened. So in the end, we circle back to where I grew up and crawling through caves, and I see it in a completely different way from where I was 30 years ago. And so it's very important, as in a lot of science, to revisit some of your old stomping grounds and see it through a new eye. And it gives you a completely new viewpoint on how things occur. I want to thank you very much for listening today. Lots of support over the years, lots of funding, lots of helpers, lots of co-authors, and I'm certainly happy to answer any questions that you might have. Thank you very much for your time, and have a great day.